Okay, we're going to continue on our handout and we're going to be looking at problem 627 in our book on page 163. So if we look, it's in the first column towards the bottom here, and it's problem statement 627. And this is a device, it's a sloshing bath used to wash vegetables. So this is kind of like the basket, if you would, that they would go in. And then we've got a crank that's going to go around and this is going to oscillate back and forth. Okay. The configuration shown, use the relative velocity method to graphically determine the angular velocity of the water bath. So this is the water bath. We want to know what is the angular velocity of that. Okay. And it says, as the crank is driven counterclockwise at 100 RPMs. So counterclockwise is going to be going this way, right? And it's going to be going 100 RPMs. So as we know, first things first, we need to draw this kinematic diagram in AutoCAD. So we're going to have our frame here. First connection to the frame, we're going to have the crank. It is 80 millimeters long. It's 75 degrees. Then we've got our connecting rod, 800 millimeters long. And then our other frame connection is 1200 millimeters to the left, 120 up. And this is going to be then a length of 720. Okay. So I already have mine drawn in AutoCAD. So I will let you take some time to get that in place. So mine looks like this. I used my start file for millimeters because that's what we're working in. And then I think I even scaled this up 2 times because it's like 1200 millimeters rather than like 300. So I did make it a little bigger. So I'll let you go ahead and get started on getting the kinematic diagram in place in the arrangement that we see there in that problem in the book. Make sure as you're doing that, you're using your standard symbols as well as labeling your links and your joints, because we'll be referencing those in our equations and such. I think I did that. So what I did for my start file, so our original start files were in inches, right? What you can do is you can save it as a millimeters. And what I did was I simply took that file or that graphic and I scaled it up 25.4. And then I saved it as millimeters. And then I used that kind of as my start file then. And that seemed to work really well when my distances were like 300 or 150. But now that we've got the one that's 1200, then I had to kind of scale this up a little bit more again. And then I saved it as problem 627. Just remember, it's not so much the size of the text and that it has to be exact. It's when you do your screenshot, can I see everything? That's the important part. So make sure that if you have to make it, larger, you can just scale those up. Make mine a little bit larger so you guys can see them a little bit better. You guys are. think that's better sizing so that you can see what we got here. And then remember to add your mobility equation to verify that the number of links and the joints that you have there shown are correct, because your F should be equal to 1. How many are still working on the, okay, good, 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 good. I'll give you guys time. Seems like there's less clicks. How are you guys doing? Who's still working on the diagram? Anybody? I'll check the chat box as well. Anybody still working on the diagram? All right. Okay, if not, then once we have our diagram in place, we have 4 links and 4 joints, so our mobility equation comes out to 1, okay? This sets the directions for our velocities, right? So let's go back underneath our camera and kind of look at our problem. So the problem wants us to determine what is the angular velocity of our water bath. The water bath is represented just by, a line, link number 4. So we're wondering, is this going clockwise, counterclockwise? What W4 is? What is the angular velocity of that? Now, we know how fast our crank is going. It's going 100 RPMs counterclockwise, okay? And that's link number 2. Link number 4 is not directly, on it. It's connected to it, but it's going to go through this link VC, or I'm sorry, it's going to go through link CB. So we need to use the relative velocity equation in order to get to the velocity of C, which then we can use to find W4, okay? So I'm going to go down to the velocity of C here. I don't know if calculate's the right one. I think it's determine VC using the relative velocity method, okay? The relative velocity method. So that means that we're going to be determining it using that vector equation. So it's going to be VC is equal to, this is our unknown, the velocity of B, which is going to end up being fully known up here, magnitude and direction, plus vectorially the velocity of C relative to B. Now, let's start by looking at the velocity of B. The velocity of B is on the crank, which is rotating counterclockwise at 100 RPMs. So we want to show the velocity of B on this link on its endpoint. So it is going to be perpendicular. It's kind of close to that, but I'm going to kind of show it going off. It's going to be perpendicular to link number 2, going in the direction of rotation, okay? Now that's going to be its direction. Its magnitude, we can calculate by using the velocity equation. VB is equal to W2 times R, or the radius, the distance to point B. Now, our W2 in this equation, we're given the value of 100 RPMs, but we can't use that here. So we need to first do that conversion into radians per second, and then we're going to put it into our W2. So go ahead and convert the 100 RPMs into radians per second. And once somebody gets an answer, let me know what you get for W2 converted to radians per second. 10.47, is that right? Radians per second. 10.47 radians per second. Everybody get that? Okay. Remember, no news is good news to me, so make sure you're on it if you have a question. Now, this is going to be the value we're going to put down here. So our VB is going to be equal to 10.47 radians per second times the length of this link. So we've got to look back at our original diagram, and that was 80 millimeters. Okay. So our velocity at B, its magnitude, tell me what you get. Okay. 837.7.76 millimeters per second. So when we multiply radians times millimeters, because this is like over 1 here, the radians drop out. Okay. So now that we know the magnitude of B and we know its direction, we can kind of put 2 check marks on top here, right? Because we know VB is fully defined. Let's look at VC relative to B. That's the next one after B. So the velocity of C relative to B is going to be the velocity of this link right here, okay? And it is going to be perpendicular to the line. So its line of action is going to be, oops, wrong one. This is C to B, sorry. The velocity of C relative to B, velocity C relative to B is going to be on a line of action that is perpendicular to the link connecting C and B. And we don't know if it's going to go up and to the right or down and to the left, right? So we know direction, but we don't know magnitude. So we can say we don't know its magnitude, but we do know its direction. Okay. And then lastly, we need to find the velocity of C, which is on the end point here of link number 4. And as we look here, we know that the direction of a velocity is always going to be perpendicular to that link, okay? But it's going to go through point C. So that means that it's going to be something like this. And chances are, if I'm rotating this on our driver counterclockwise, this too is probably going to go counterclockwise, probably. And so this is going to be the line of action for the velocity at C. So if we look down here, we don't know the VC's magnitude, but we do know its direction. So again, just verifying that even though we have 2 unknowns, magnitude of VC and the magnitude of VC relative to B, they have to be separated on either side of the equal sign. So now, since they are, we are ready to kind of take it to that next step. So let's go back to our AutoCAD. I'm going to scooch over here. Okay, scooch over here. So now as we look at this diagram, let's see what I have here. I have the velocity of B going up and to the left. It is perpendicular to link number 2. And it's going, right through the end point of link number 2 where the point B is. Its length is the length that we calculated. So 837 point, I got 0.7, you guys got 0.76, so you can add that extra decimal place, okay? And it is going to be going up and to the left. So I have it labeled and I have it dimensioned. The other two lines that I have here, the velocity of C relative to B, this is a line perpendicular to link number 3, which is the link that connects points B and C. And then lastly, I've got the velocity of C perpendicular to link number 4, and I have it going through point C. So that's its line of action. Notice I don't have an arrowhead on there, but it's probably going to go up and to the left. So I'll give you a chance to get those in place. All right. And then also adding the labels, making sure they're large enough. Now, again, this can be added to this original diagram over here as long as you have the labels and you don't have crossing things over. So you can add those items right here. All right, they can all be on the same diagram. You don't have to have separate ones unless you want to. Anybody still working on the velocities? Okay, take your time. This is a long process, so hopefully everybody's getting what they need here. Now, once we have our velocity lines of action and our known velocity, in this case, VB, all set, now we're ready to do our vector diagram. So I'm going to do this down here again so that we can, so you can see the process that I went through. I think that's important. So I'm just going to copy my vector equation down here. And I'm also going to add, just see here, I'm going to add an origin. So okay. So I'm going to put my origin down there. Now, as we know, I'll go back over here. We look at our vector equation. We're going to start where we know the most. And where we know the most is the magnitude and direction of velocity B. And that's our first variable on the right-hand side of the equation. So I am going to copy my velocity of B. I guess I'll add the dimension as well. Oopsie. Got to get the arrowheads too. So I'm going to grab velocity of B. Okay. And I'm going to grab the end point. So make sure you use your object snaps. And I am going to put that at the intersection of my origin. Okay, so that's my first vector in my vector equation on the right-hand side of the equation. Then on the end point, I'm going to add the direction of C relative to B. So I'm going to copy this line. And I'm going to go from that endpoint or anywhere along. I'm going to add it to the tip of that vector, my vector BC, or my vector VB. Okay. Now I've exhausted what I can do on the right-hand side of my equation. So I'm going to go over that equal sign and I'm going to place my velocity of C. So my velocity of C, I know my line of action. I'm going to copy that, its label, endpoint, and I'm going to go to the origin with its tail. Okay. Now you can see there's going to be an intersection that's going to form up here. So I'm going to do an extend to that. And then I'm going to trim that little extra that's there. Okay. So you should have something that looks like this. And again, using lines that are perpendicular to the appropriate links here in our in our kinematic diagram. So that's why we have to draw a good kinematic diagram to start, and then we're using that to get these directions. Now, arrowheads. Let's start with the velocity of c relative to b. We took VB plus vectorially VC relative to B. So that means the arrowhead or the tip of C relative to B is going to be here. Right there. Oopsie. And then we cross over the equal sign. The tail of the velocity of C is going to start at the origin, and its tip is going to go to the last vector, which is on this side. So here is the arrowhead for VC, which confirms what we were expecting. If this is going to be going in a counterclockwise direction, we were expecting that to then move that very same way, counterclockwise, which is good. Now, the magnitude of velocity of C. So I'm going to go to my notes, and I'm going to go to my annotations. I just want you to know that, remember, when we put our dimensions in here, that dimension is probably going to be pretty small because we had to scale these things up quite large. So I'm going to go to modify, and I used on my fit tab an overall scale of 200, okay, on this one. All right. So if you need to change that, that should get you close to what you need. Okay. And now I'm going to do an aligned dimension, one endpoint. Make sure you get the endpoint. And I have perpendicular as one of my object snaps because of the perpendicularity stuff. And then you're going to notice that I got 815.1139 in my case. Yours might be off a little bit on the decimals because you had an extra decimal place on B. Okay. One seven. Yeah, you probably had that extra decimal place up here. So. Okay. And then making sure that your labels are here and such. So what you would have to like hand in as far as the AutoCAD stuff, I'm going to say is like the middle part here. Okay. So you need a vector diagram with your mobility equation, all of your labels, your velocities, whether they're lines of action or they're actual vectors, and then your vector equation labeled with the dimension of the items that you need. Make sure when you do your screenshot and you add it to your document that I can see the values. This is where it gets a little tricky, so double check those and, you know, make these dimensions, like I said, really large in their scale because otherwise you're not gonna be able to see them. Okay, so now that I have that 815, I'm really done with the AutoCAD now. I'm done with the AutoCAD. So I have the velocity of C. I'm going to go back to my calculation here. So I know that the velocity of C was equal to 815.11 millimeters per second. So that was dimensioned from my vector diagram. Okay. Now remember, this is not a slider crank. We still need to find the angular velocity of our W4, okay? Now, we already know and we'd confirmed that the direction of the velocity of C was going up and to the left. So if we hold this at point D and we pull, our W4 will be going in a counterclockwise direction, just so you know, okay? So now we just need to calculate that value, all right? How am I going to do that? How am I going to find W4? I know the velocity of point C, that endpoint right there. I know how long this is from my diagram. It's 720 millimeters. What is the equation that I'm going to use to calculate W4? Velocity of C divided by, you're correct, Lex, R 4. Oh yeah, thank you. Thank you, Jack. I see you put it into the chat as well. Make sure that you use the corresponding variables. Since we're trying to find the angular velocity of the water bath, that's our link number 4. And the velocity that we're using is going to be VC. So now we're going to put our values in here. So we've got the 815.11 millimeters per second divided by 720 millimeters. Okay. And this 720 is off of the diagram. Millimeters cancel out. So we're going to be left with, it'll be radians per second for units, correct. And what is our value? 1.13. I got 1.132, maybe, I don't know. Again, our little decimals might be off a little bit. Radians per second, correct, because it's millimeters cancel, so it's nothing per second, but radians magically appear for us, right? So am I done? Done. I've got W4. Lex says, no, you're not done, Kelly. Darn it. Thought we'd be done. Oh, yeah, we will put a box around a value, but this isn't the one yet. What do we need to do? Exactly. So even though we're close to the end, we want to convert this to revolutions per minute, so RPM. So go ahead and do that. Convert this to your revolutions per minute. Now we're going to put a box around your RPMs. Make sure when you show your work here, you show the conversion in ratio form. Do not do it any other way. I want to see the cancellations. It's very important. Same thing here. Units have to be in all phases of the problem and canceled out and or combined. There's one more thing we need to add, and that is just telling us that this is counterclockwise. Okay, we want to put the direction on there. Okay, any questions at all? Right. How do you feel about relative velocity? Slider cranks, that was the previous problem that we did. We've got a good example there. And we also have these oscillating, finding the W's of output links. Questions at all at the moment? Yeah, you want to look at the homework? Because I'm debating. I had originally planned, see, it's a democracy here. I had originally planned that we would do example 6.6. Does anybody want to do 6.6? Josh is like, no way, Jose. Let's just take a peek at it. Let's take a peek at it. And I'll just show you what it's like. It is similar to the very last problem that we just did. So if we go to page 131, here's the rock crusher. And we've done this one before as a homework problem. But here is the rock crusher, and they want us to find what is the angular velocity of the crushing ram. So in this case, we've got a crank over here. We know how fast it's going, connecting rod, and then we've got our crushing ram right here. And it wants to know what is the angular velocity, the W4, if you would. So it's just like the very last problem that we did. I'd be happy to do another one. Does anybody want to see another one? Oh, Jack said, let's do it. He is very eager. Okay. I think it's a good idea too. I had originally planned it. This is what I'm gonna do. I'm gonna make it an optional practice problem. So if you want to follow along with me, you can to get extra practice. Otherwise, you can move to the homework. And I know Lex was excited about looking at the homework. So let's take a peek at our homework really quickly. And then we'll come back to this extra practice problem. Jack, it might just be you and me. And that's okay. You might change your mind after you look at the homework. You might feel like, oh no, we need to start that. All right. So if you remember the last time we were together, Practice is good. It really is, Jack. I agree. I'm all about the practice. So you'll remember the last time we were together, you were able to do problems, all of the problems up through 612. Okay. So I think there was a total of 8 there. So the last 4 problems that you're going to be doing are going to be the relative velocity method that we've been looking at. Okay. So you're going to have number 21, 23, and 28. Okay. And 31. So let's take a peek at these at the end of our chapter. And what I'm going to do is this. I am going to stop the recording here because I think it's nice to have a separate assignment overview video. And then that way you can go to that directly rather than trying to find it in the video. So I'm going to stop recording.